Slide 1. Greetings, students, and welcome to today's exploration of an intriguing problem in the realm of algorithms. Today, we delve into LeetCode Problem 3, which challenges us to identify the length of the longest substring devoid of repeating characters from a given string. Imagine we are presented with a string that may encompass letters, digits, or various symbols. Our task is to meticulously examine this string and determine the maximum length of a contiguous sequence of characters, ensuring that no character appears more than once. For instance, consider the input string ABC ABCBB. Here, the longest substring without repeating characters is ABC, which possesses a length of 3. Although alternative substrings such as BCA and CAB share this length, ABC is the first occurrence we encounter. Join me as we unravel the intricacies of this problem and discover the elegant solutions that lie within. The sliding window technique is a powerful algorithmic approach that helps us solve problems involving contiguous subarrays or substrings efficiently. Imagine a window that can slide over a dataset, allowing us to examine a portion of it without having to check every single element multiple times. This method is particularly useful when we need to find patterns or specific conditions within a range of data. At its core, the sliding window technique typically uses 2 pointers that define the edges of this window. Initially, both pointers start at the beginning of the data structure. The right pointer moves to expand the window, while the left pointer can be adjusted to shrink it when necessary. This dynamic adjustment helps us explore the dataset thoroughly, ensuring we consider every relevant subset while avoiding redundant calculations. By reducing the need for nested loops, the sliding window technique enhances both efficiency and clarity in solving various computational problems, making it an essential tool in areas like text processing and time series analysis. The code on this slide demonstrates the sliding window technique, particularly applied to the problem of calculating the sums of all contiguous subarrays of a fixed size, k. First, we initialize a variable called windowSum to keep track of the total of our current subarray, and an empty list named result to store the sums of each window we calculate. Next, we compute the sum of the first k elements in the array using a simple loop. This gives us our initial windowSum, which we then add to the result list. Now, here comes the sliding part. As we move through the array, we add the next element and subtract the element that is now outside of our window. This allows us to efficiently update our sum without having to recalculate it from scratch. Finally, we append each new window sum to our result list and return it. This method efficiently computes the sums in linear time, making it a powerful technique for similar problems. Character frequency mapping is a powerful technique used to count and keep track of how often each character appears in a string. Imagine you have a box of different colored marbles, and you want to know how many of each color you have. You'd create a list where each color corresponds to a count. This is similar to what we do in character frequency mapping, where we use structures like hash maps or dictionaries to store characters and their counts. This method is especially important in areas like natural language processing and data compression. By knowing how often characters appear, we can identify patterns, create histograms, or develop efficient encoding schemes. Essentially, it helps in optimizing how we process text. The process is straightforward. We loop through the string and update our character counts. This operation typically runs in linear time, ON, which means it scales well with larger datasets. Once we have our character counts, we can gain insights into the data, like which characters are most frequent or how they're distributed. This foundational concept is crucial for more advanced algorithms and machine learning, where understanding character or word frequency can significantly impact performance. In this slide, we are looking at a function that creates a character frequency map. This is a helpful tool for analyzing how often each character appears in a string. First, we start by initializing an empty dictionary called frequency. Think of this dictionary as a container that will hold each character as a key and its count as the value. Next, we iterate through each character in the string S. If we find that the character is already in our dictionary, we simply increase its count by 1. This is like keeping a tally for how many times each character shows up. If the character isn't in the dictionary yet, we add it with a count of 1. Finally, we return this frequency dictionary. For example, when we use this function on the string hello, we get a result of H1E1L2O1. Here, the character L appears twice, while all others appear once. This mapping helps us understand the distribution of characters in the string, which is essential for solving problems like finding the longest substring without repeating characters. The two-pointers approach is a powerful technique used in algorithm design to efficiently traverse data structures like arrays or linked lists. Imagine you're trying to find a specific item in a long line of people. Instead of asking each person one by one, you could send two friends from opposite ends, allowing them to meet in the middle. This strategy saves time by reducing unnecessary comparisons. In terms of complexity, many problems traditionally require O(n)-fold time, especially when using nested loops. However, with the two-pointers technique, we can often reduce this to O(n). This is because we systematically adjust the pointers based on the specific requirements of the problem. For example, if we're looking for pairs that sum to a certain value, one pointer could start at the beginning of the array, while the other starts at the end. By moving the pointers towards each other based on their current values, we efficiently hone in on our solution without extra complexity. This technique not only streamlines the process, but also enhances scalability, making it a valuable tool for any computer scientist. The function we're looking at uses the two-pointers technique to process an array. First, we initialize two pointers, left, which starts at the beginning of the array, and right, which begins at the end. This setup is crucial as it allows us to traverse the array from both ends simultaneously. Next, we create an empty list called result to store our outcomes. The core of our logic is in the while loop, which continues as long as the left pointer is less than or equal to the right pointer. Inside the loop, we add the values at both pointers together and store that sum in our result list. After recording the sum, we move the left pointer to the right, effectively progressing through the array, while the right pointer moves left, closing in towards the center. Finally, once we've processed the entire array, we return the populated result list. This method is efficient and visually intuitive, allowing us to gather sums from both ends toward the middle. LeetCode problem 3, titled Longest Substring Without Repeating Characters, requires us to find the length of the longest substring that contains all unique characters from a given string. To solve this, we start by initializing some variables. First, max length keeps track of the longest unique substring we've found, starting at 0. We also create a set called charSet to store the unique characters in our current substring, and a variable left to mark the start of that substring. Next, we loop over the string using a variable right, which represents the end of our substring. If the character at sRight is already in charSet, we have a duplicate. This means we need to move our left pointer to the right until there are no duplicates. After ensuring the character is unique, we add sRight to charSet and calculate the current length of our substring. If this length exceeds max length, we update it. Finally, after checking all characters, we return max length, which tells us the length of the longest substring without repeating characters. The example code provided illustrates this algorithm efficiently, using a set for fast lookups and a two-pointer technique to manage our substring boundaries, achieving a linear time complexity of O(n). In this problem, we are tasked with identifying the length of the longest substring without repeating characters from a given string, S. A substring is defined as a contiguous sequence of characters, and our goal is to maximize its length while ensuring no characters are duplicated. Notably, the string can have a length of up to 50,000 characters and may contain a variety of characters, including English letters, digits, symbols, and spaces. These constraints will guide our approach to finding an efficient solution. The Python function lengthOfLongestSubstring tackles the problem of identifying the length of the longest substring without repeating characters in a given string, S. It does this using an efficient technique called the sliding window. We start by initializing a dictionary, charscoreIndexMap, which keeps track of the most recent index of each character we encounter. Alongside this, we use two integer variables, left, marking the beginning of our current substring, and max length, which stores the longest unique character substring we've found so far. As we iterate through the string with a for loop, right represents the end of our current substring. When we find a character that's already in char index map, it signifies a repetition. To maintain uniqueness, we adjust our left pointer to the index right after the last occurrence of that character. This is done using left equals max left char index map s right plus 1. After updating the character's index in char index map, we recalculate max length as max length right s left plus 1. Finally, the function returns max length, representing the length of the longest substring without repeating characters. This entire process runs in ON time thanks to the efficient lookup capabilities of dictionaries, making it optimal for this problem. The time complexity of the problem, longest substring without repeating characters, is ON. This means that as the length of the input string increases, the time it takes to find the solution grows linearly. We achieve this efficiency because we only need to make a single pass through the string. During this pass, we track the characters we encounter and their positions. Next, we look at space complexity, which is O min n m. Here, n represents the length of the string, while m denotes the size of the character set. Essentially, we use a hash map or set to store characters and their indices. The space required can grow to the number of unique characters in the input. If we have a small character set like only lowercase letters, the space usage might be limited, even if the string is long. This balance between the string length and the character set size is crucial for understanding our algorithm's efficiency.